welcome to Computability Freaks. I'm your host, E.C. Slater. You might know me as the star of the hit television show Computability Freaks. Why don't you come with me on this journey through Soare's The Art of Turing Computability, Theory and Applications. Today's episode is Introduction. Joining me today is Miss Evie. How are you doing, Evie? Okay, good. Good to hear about that. So I say first of all, we're gonna go through the introduction today, and then next time we'll probably get into the main text. I'd say that in order to understand the introduction, we should read the whole book. Okay, so we'll just do like a little bit of the introduction. I'll tell you about the introduction, and so we'll do some other things. Okay. So. Okay, in the introduction, so the first section of the introduction is the one that we'll go through a little bit more, and that's Turing machines. And it's called an A machine. Okay, this is a idealized typewriter. There's infinite tape. And the head moves back and forth one cell at a time. Okay, so here's the tape, and okay, this is the introduction. So like we're gonna probably be going into all the details, but let's just sorry. I'm like sometimes I just can't draw a straight line if I don't get the right angle. Okay, so this is it kind of looks like a belt or something, but so this is the head moving back, and okay, maybe I should have drawn it over there, but let's say it's in the start state. It's in some kind of a mode. What is the mode? I'm moving to the right. I look at this, I move to the right, or something like that. Okay, so it's, so how and where it moves, how and where this, the last time we saw, like, the fact that Turing sort of saw this as a machine and worked with it like a machine, that was extremely helpful. That was a helpful move in terms of computability. Okay, so how and where it moves depends on its state. So or like a state of mind, you know. It's a finite state program. So how it moves depends on the state. Okay, and yeah, I'm glad to be here, you know. And okay, it's good to see you. Okay, so maybe the state of mind might be. I'm saying more general. If I was going to say this, how the Turing machine would actually do this, okay. I'm just saying maybe my state of mind is I'm adding two numbers, and once I add the two numbers, I'm going to produce the results. Okay, that's actually maybe complicated to write as a, how we're going to do that as a Turing machine, but that's the idea. So right now I'm adding two numbers, okay, something like that. Okay, I was just going to insert this, this idea of computer. So it's you're trying to emulate, if that's the correct word, a computer. And at the time, a computer was a person that was maybe a woman sitting at a desk with a piece of paper and making computations. Okay, so like they had to figure out maybe some integral or something, I don't know. And they just need to figure out the integral that someone's going to do that work for them. Okay, so this is like, we're trying to emulate this idea of a person writing a piece of paper. Okay. Okay, in 1936, Okay, Turing demonstrated convincingly this mathematical model captured informal captured the informal notion of effectively calculable. So this idea of the Turing machine we're getting an overview here, I think. Captured informal. Oh, I was thinking of what I was thinking about earlier. Informal notion of effectively calculable. Okay, I was gonna say, it's like he made it real. I feel like when you make something real, I think about like this, the realm of mathematics and this like, is it real or not? I feel like thinking of it as real and like as a machine is extremely helpful, and it might just be, I've heard other people say like a freedom of words. Being free to imagine this is actually helpful mathematically to get the ideas going. Yeah. So I also think of it like, if you can somehow think of, mathematical objects as having like some character, some kind of personality to them, it can be a lot easier to work with or imagine or something. Yeah. Okay. So I guess I had to look up the word effective. It's like, okay, let's just see what does effective mean, because we see this word a lot: effective computability, effective calculability, effectively calculable. Just looking at online, just what the definition: successful in producing a desired or intended result, or fulfilling a specific function. In fact, though not formally acknowledged as such. So I would say that effective calculability means that it's successful in producing a desired or intended result. So I'm just going to put successful, maybe even correct, because I'm thinking now about like these ChatGPT and stuff, and it's this big autofill, but it's not effective. I'd say it's not like you can't depend on it to calculate things, right? This is kind of when I'm thinking about those things. That's okay. Not to say it's maybe not helpful. It's just that okay. I think effective calculator, like a reliable calculator or something. Okay. So effective uses an algorithm. Well, maybe that's true. Okay, it's kind of hard to talk broad picture like this. Okay, so we'll, when we get into the math details, maybe it's a little easier. Okay, ever since 1936, Turing's model in analysis has been accepted as the model for computability. So Turing model. Most convincing model. And the results of this book are based on Turing's model of computability. It's accepted today. It's computers that exist now. So, okay, the book is based on Turing's model of computability. Okay, so note on the introduction, again, we're learning the entire book, so it's, maybe it's interesting if you already know about it, or, it's still interesting. It's maybe a little, like, not satisfying, because it's kind of vague. Okay, so I'm going to talk a little bit about the next section, even though that's a little later in the book, the Oracle machines and Turing reducibility. So, but we'll talk about those a little bit. Okay, this is another section in the introduction. So, okay, after the 1936 paper, Turing went to Princeton and did a PhD along with Alonzo Church. Okay, it looks a little weird in my spelling there. Just want to make sure. Yeah, Church. Okay, Church Turing thesis. That makes sense. Okay, so after 1936 paper, Turing PhD with Church about ordinal logics. Okay, and this is very interesting, and like reminds me of infinite chess and stuff, because we're talking about the supremum of all computable ordinals. What's that thing called? Okay. Oh, I was looking at a different thing with that. Yeah, ordinal logics, that's interesting. Okay, so like, computable ordinals, computable, and then the omega 1 CK, the supremum of all computable ordinals. So he's doing ordinal logics. Okay, I really apologize that I like we should talk sometime, like in detail about like what the computable ordinals. That's a whole different, interesting topic, maybe. Okay, and I feel like I'm not doing it justice at all. A computable well ordering of a computable subset of natural numbers. Okay, that's extremely interesting stuff. Okay, so we talked about post and about this Turing reducibility. So A, the 3 lines, T means Turing equivalent. Okay. If A A is Turing reducible. You can compute A using B as an oracle. Let's see if I missed something here. I did miss something. Okay, okay, just a sec. I missed a page in this. So in 1938, it's funny because I'm like pulling stuff from. Okay. Yeah, post defines set B to be Turing reducible to set A. Okay, but we're not actually there. I wrote something else here. Okay, I must have looked something up. Okay, I think it's just that in the dissertation there's one line about an oracle machine. Okay. Okay, so I'm just going to skip this. I'm just going to say, okay, so I'm not exactly, oracle machine. Turing just mentions this, okay. called an O machine. This is of greatest importance and ends up being really, really important in computability theory. Okay, so imagine our tape, and we have the head of the tape here. But the program can ask questions to an oracle. Okay, so we could go over here, we'll do like a crystal ball here. It has this information. And what it's really got is a tape written on it, the characteristic function of a set. So it's got, let's say it's got B on here written, some set, okay. So we think now it would be like you have a laptop that you're working on, and the laptop is like a local server, and it's connected to the internet, where there's lots of information, and this is a larger database. Okay, we can't store the whole internet on the laptop. Okay, so this is a similar idea to the Oracle machines. And so now I can remember what's. Okay, I do these like I take these notes like ice cream shop is so nice, enjoyable that I kind of forget what I write. Okay, so this idea lay dormant until Post in 1944. Okay, so then Post 1944 kind of revives the idea. Okay. B is Turing reducible to A if there's an oracle machine which computes B when the characteristic function of A is written on the oracle tape. B, let's write it down. B is Turing reducible to A if there is an oracle machine which computes B when the characteristic function of A is written on the oracle tape. Okay. And any oracle machine is just an ordinary Turing machine if you just put nothing on the oracle tape. It's just like, just cloudy, just put a cloudy crystal ball. There's nothing to look at. But oracle machines can do much more. So an oracle machine is a normal Turing machine if you put nothing on the tape, but it can do much more. And so Soare says, in computability, results are not about computable functions on computable sets, but compare non-computable sets, or undecidable sets, A and B, with respect to relative information content. So this is from Soare. In computability, results not about computable functions on computable sets. But about comparing relative information content of non-computable sets. A and B. And this is also called undecidable. Okay. So this A Turing equivalent to B means that they code the same information. That's nice to know, because I do always hear about Turing computability and those computability talks. And it's like, oh, that's what the main stuff's about. Okay, okay. Turing degrees is going to be in section 3.4. We're going to talk about what's in this book today. Equivalence classes containing sets with the same information content. Okay, so the rest of the introduction, I really feel like even that we should have, we really need to read the book before we read this. So I'll just mention what the other sections are and talk about the book a little bit. Okay, so the introduction. So Turing machines was the first part of the introduction. Oracle machines and Turing reducibility was the second. Computable enumerable sets is the next section. So let's wait on that. And let's look at the book, what we're actually doing here in this, when we meet. Okay, so I don't know if you can see that. Let me just... I don't think it's that important that you see the contents. It's probably, if you have the book, you can see them. But the point is that there's a lot of sections, and my goal is to get through just the first section, defining computability, this semester. Now that's only 20 pages. Maybe we'll move a little faster. Maybe we'll get into computability and enumerable sets, but there's no reason to rush. But this might take a little while, so we'll maybe be here for a while. That's my goal, though, just to really get a good handle on the computability, to get a good handle on defining computability. And we can see there's lots of interesting stuff. Okay, so the intro, so let me say the other sections that are in the introduction. So the introduction is a summary of part 1 up to chapter 7. And the other, so the other sections in the intro are, there's computable enumerable sets, bounded, Turing reductions. Okay, I'm suddenly feeling a little bit cranked up. Okay. Okay. Finally, understanding Turing reducibility. Priority arguments. That looks interesting. Okay, and then another section that's in the intro is other parts of the book. Okay. And in this part of in this section, he says that the summary, chapters 1 through 7, is in the intro, which we just skimmed through, and the summary of the rest of the book is in the next section, how to read the book. Okay. We need to read the book to understand the intro. So I just will mention what's in the how to read this book. There was a couple. We need to like know a lot more, but there's a couple things that I thought we should just play around with a little bit. Okay, so the part 1 of this book, maybe we'll get to in a few years. The core subject of computability is chapter 1 through 7. And this is from the definition of Turing machines up to finite injury methods. Okay. So, and then part 2, which really looks interesting, is trees. And pi 1 0 classes. Many times in my life I've been really very confused and realizing that I have a different definition of a tree than the one I was supposed to be using or something. Okay, so there's lots of trees. This is the first sentence in that section, and it's just a definition, so let's just copy it down. A tree is a set of strings closed under initial segments. And a pi 1 0 class is the set of paths through a computable binary tree. That would be fun to look at. Okay, part 3 of the book is minimal degrees. Part 4, which looks very interesting, is games in computability theory. This really reminds me. Every time I hear the Infinite Games Workshop, Infinite Mastermind, it just always reminds me of computability. But it's I don't exactly. They just feel really similar to each other, right? And so I would like to talk more about that. I think we should jump forward sometime and talk about games and computability theory when the time is right. Okay. So I'm still I can't help. I have to go through every section. Okay, so just so we can at least, I hope we're not missing anything. But he does point out that there's different book sections, and he gives little symbols for it. So 1 star is most important. So this is book sections. I don't know why. I used to have somewhat good handwriting. Okay, so most important. I just have to slow down, but that's no fun. Okay, most important. 2 stars is very important. Oh, most important. That makes sense, right? Most important. It's 2 stars. I remember what happened when I was reading this. I was going over these notes yesterday. And I remembered a dream that I had. I'll tell you in a second. So then there's no marking. This is average importance. empty set sign, skim, or defer till later. Okay, let's see if we... I'm not even gonna... I really want to find where he put that symbol somewhere. Okay, characterizing low 2 sets, okay. Hyperimmune, free degrees, nice. Okay. Then this symbol is difficult exercise. Do not assign lightly. And these two boxes together, this is a very difficult exercise. I saw this and I was like, oh yeah, I remembered I had a dream, and I woke up and I was like, I could see these like code over everything. Just like on the window mostly, but it's like coming through. And I could see these little symbols everywhere. And then when I was looking through this book again and getting ready for today, I was like, oh yeah, I've seen this before. It was in this book, that little symbol right there. I saw that little symbol in the dream. Okay, so maybe I was dreaming about this. The notation will be introduced as needed, he says. So, but he gives us a little hint, and I'm just going to mention, why not? It's a great place to start. So the first thing is omega. The numbers 1, 0, 1, 2, 3. The universe of non-negative integers. Okay, it reminds me of, like, I told you I wrote this paper. I submitted it. First of all, I want to mention that I didn't really expect that when I would submit this paper that as is it would be like, the Journal of Symbolic Logic or something. I didn't really think that, but I also didn't know what to do with it. So maybe I will be able to present at a conference. Okay. I don't know if you're like, I sent to Computability in Europe. Okay, that was the suggestion that I got. But anyway, this reminds me, so I just want to say, like, I am like, I wasn't like, oh my god, I can't believe this paper wasn't published. I didn't expect anything to happen to it. So I like the idea and everything, but it just felt like it wasn't like, there's not like a lot there, it feels like. But anyway, in the paper, one of the criticisms was I said it was like non-deterministic infinite time Turing machines, and at some point I said, like, all these multiple worlds that you're in, or multiple universes, because that's maybe because it's more exciting to say that way, but they said it was too flowery, is that the word? I don't know if that's the word. I agree with that too, though. It's, not to be too, like, if someone's really straightforward, that's really good. But I just, the universe of non-negative integers, we like to use the word universe when we can, okay. Anyway, so I just say, I just want to be a part of the mathematical community. That's all. As long as I'm doing something. Okay, so AKA the natural numbers. Okay, and so most of the objects. Okay, I'm going to draw this. So here, let me come down here. So most of the objects. Let's say I'm just going to make up an object here. This is another symbol that I see sometimes. I think not that one. I think there should be a little bit more room for kind of magical thinking or something. Okay, so let me see if I can draw this, what this symbol is. Okay, this is a symbol that I also see. This symbol reminds me of like light reflecting on water, trying to capture what that looks like, and it kind of like bounces around. I don't know. So this is a symbol that comes up. I think it's like flux capacitor or something. So most of the objects we study, so I put this object associated with some n in omega. So we take this object and we associate it with some number. And it's called a code number. Or a Gödel number. That's what is mentioned in the book. I've also heard it as a Gödel code, I believe. Gödel code. And this is one of the like revolutionary things that Gödel did, was like turn everything into numbers. Okay. So we have these objects. And we're going to do some operation on them. And so we're going to do some operation on objects. And maybe I do some kind of operation on this object, and it turns into this. I also saw this symbol. And it becomes some other object. So we think of this as a function from omega to omega. I turn one object into another object, and they both have codes. Okay, great. So that's that part of the introduction. So next time we'll be able to get right into the content, the main text. I just wanted to mention in the acknowledgments, he's thanking people, and I'll just mention the people that I know, because he said he's thanking his University of Chicago colleagues. And he mentions Carol Lang and Russell Miller. And then, then to Russell's student at Queens College, CUNY, Rebecca Steiner. That's nice. Okay, you can read the other things in there. Okay, so now it's time for the dramatic part of the show. So I thought we're going to be here together for a long time, so why not? Well, we should make it through Turing's and post paper. I mean, maybe just one paragraph at a time. Okay. So I'm going to read these, not trying to imitate them. Turing, there's no recording of his voice. So there's no recording of his voice. That's unfortunate, and I think we all know there's this story of Turing, and it's kind of, that's a difficult story. So, anyways, that's not what I want to talk about. But it's I can't find a recording of his. So I'm just gonna read it it's an embodiment. It's somehow inspired, but it's not trying to imitate Turing or anything. I'm just reading it. But okay. So this was, let's see what this is. This is on computable numbers with an application to the Enchendung's problem. I feel like I've heard that before. By A.M. Turing. Received May 28th May 1936. Read 12th November 1936. The computable numbers may be described briefly as the real numbers whose expressions as a decimal are calculable by finite means. Although the subject of this paper is ostensibly the computable numbers, it is almost equally easy to define and investigate computable functions of an integral variable, or a real or computable variable, computable predicates, and so forth. The fundamental problems involved are, however, the same in each case. And I've chosen the computable numbers for explicit treatment as involving the least cumbrous technique. I hope shortly to give an account of the relations of the computable numbers, functions, and so forth to one another. This will include a development of the theory of functions of a real variable expressed in terms of computable numbers. According to my definition, a number is computable if its decimal can be written down by a machine. Thank you, Turing. Okay, post. I did not find any recording of post. I saw that he was a teacher in New York. He went to Princeton. He was a teacher, a high school teacher in New York, and then he went to City College. He taught at City College, which is like 137th and Broadway. I lived at 142nd and Broadway for a little while. Nice campus over there. So this is recursively enumerable sets of positive integers and their decision problems by Emil Post. Okay, I don't know where this accent exactly coming from or who exactly the inspiration, but this is just what came out from reading the words. And also, like, I can't always tell where his sentences are going. Like, I can't exactly tell what the structure of some of the sentences. So if I'm emphasizing the wrong parts, I'm sorry. So this is a 44. Okay. Recent developments of symbolic logic have a considerable importance for mathematics, both with respect to its philosophy and practice. That mathematicians generally are oblivious to the importance of this work of Gödel, Church, Turing, Klein, Rasa, and others, as it affects the subject of their own interest, is in part due to the forbidding, diverse, and alien formalisms in which this work is embodied. Yet without such formalism, this pioneering work would lose most of its cogency. But apart from the question of importance, these formalisms bring to mathematics a new and precise mathematical concept, that of the general recursive function of Herbrand, Gödel, Klein, or its proved equivalents in the developments of Church and Turing. It is the purpose of this lecture to demonstrate, by example, that this concept admits of a development into mathematical theory, much as the group concept has been developed into a theory of groups. Moreover, that stripped of its formalism, such a theory admits of an intuitive development which can be followed, if not indeed pursued by a mathematician, layman, though he be in this formal field. It is this intuitive development of a very limited portion of a subtheory of the hoped-for general theory that we present in this lecture. We must emphasize that, with a few exceptions, explicitly so noted, we have obtained formal proofs of all the consequently mathematical theorems here developed informally. Yet the real mathematics involved must lie in the informal development. For in every instance the informal proof was first obtained and once gotten, transforming it into a formal proof turned out to be a routine chore. So he says, for general recursive functions, see 9, 8, 12, 11 for Church's lambda definability, 1 and 6 for Turing's computability, 24, and the writer's related 18. To this may be added the writer's method of canonical systems and normal sets. See page 3942 and bibliography of 6 for a survey of the literature and further references. Numbers and brackets refer to the bibliography at the end of the paper. Our present formal proofs, while complete, will require drastic systemization and condensation prior to publication. Proofs are coming. Oh, and I noticed this is very nice that this is tomorrow. So tomorrow's the 26th, I believe, 2024, and so that's 80 years ago that Post presented this at the New York meeting of the Society on February 26, 1944, by invitation of the program committee, received by the editors March 25th, 1944. Well, that's all for today. We'll see you next time on Computability Freaks.